In this video, we want to consider a common sense approach to proving Stokes theorem. Where here we have a three-dimensional vector, and we're taking the line integral of it about some closed curve, and that closed curve encompasses a solid three-dimensional figure, and this is equal to, this line integral is equal to the surface integral of the curl of our vector and taking the dot product of that with the differential area vector. That's what we want to prove in this video. And again, hopefully we have an approach. It might take a little while to go through all the parts of it, but hopefully it is an approach that will make sense. To get us started, let's suppose we have an infinitesimal path with on a differential here, dx and dy, and right in the middle of this infinitesimal path is a three-dimensional vector v that has I, j, and k components. Now v1, v2, and v3, each of these can depend upon x, y, and z. So for example, our vector v might have this expression where the ith component v1 depends on variables x, y, and z, and so does v2, and so does v3. Now what we want to do is take the line integral of our vector v about this infinitesimal path, that is along this differential path, dx, dy, dx, dy. So we would write it in general like this, say v dot dl. And just to be clear about this, remember from our introductory video on line integrals, here it's just a two-dimensional case now, but we had a curve AB in the xy plane, and this was in some vector field that constantly varies in direction and magnitude. So, for example, here we are a particular differential line segment on the curve, and the vector field has that magnitude in that direction. It'll have a normal and a tangential component, and what we're doing is multiplying the magnitude of the tangential component by that arc length there, ds, or sometimes it's called dl. We're going with this notation now. And this would just be the dot product of f dot dl, where dl is just simply the differential arc length that is tangent to the curve at that particular point right there. And also notice that the vector has to be right in juxtaposition at the curve of that particular point. So here, v dot dl, dl is just in two dimensions. dl is dx I plus dy j. So we take the dot product of this with our three-dimensional vector, we're just going to have v1x plus v2y. So the other way of expressing it is like this, v1 dx plus v2 dy. Now, let's work with this part of the expression, v1 dx. So let's consider then taking the line integral of the vector v about this segment AB. Well, to do that, this vector has to be in juxtaposition with this differential segment AB, which means we have to move it down a distance of dy over 2. And we're moving it down. Let's consider down to be negative. So the point is that V1 is dependent upon variables x, y, and z, but when we move this into juxtaposition, the y variable changes. Therefore, V1 has a certain value when it's right here in the middle of our infinitesimal path, but now when we move it down to here, V1 is going to change. So this will equal, it will be V1, what it was originally, minus the amount of change. Or we could say plus this change, but this change is negative because we're going downward. So this would be minus the partial of V1 with respect to y times dy over 2, and that's times dx. Now let's look at this. V1 dx, V1 had a certain value here, but we moved it down. So this is how much it changes. This is the partial of V1 with respect to y. That tells us how V1 changes with respect to y, times the amount of change of y. That's dy over 2. So the new value for V1 down here will be what it was here, minus this. Then we have dx. And now this is along that differential segment going A to B. Now going here to here, dx is 0. So now we're going in this direction. Now we're going from C to D, so we're going in this direction. But that means we have to get our vector in juxtaposition with the CD differential path. So that means we have to move it up a distance of dy over 2, and up will be in a positive direction. So for here, the new value for V1, and we move up to here, this will be plus. Actually, what we want to do is we're going in this direction, so we want to have a minus sign here. We were going here, now we're going here, so this will be minus. Then the new value for V1 will be what it was originally. And we're going upward now, so it's plus that amount of change. And that amount of change is the partial of V1 with respect to y, dy over 2. And we have this times dx. So again, when we move the vector v up to this differential path, CD, first we're going in this direction now, so here's a minus sign. But V1 has a value here. When we move it up to here, the new value for V1 is going to be what it was originally. This is positive, so it's plus the amount of change, and the amount of change is the partial of V1 with respect to y. That tells us how V1 changes with respect to y, times the amount of change of y. And again, these are necessary because all the components of the vector, the I, j, and k components, can be dependent upon x, y, and z. So if we change this in the y direction, it's going to change our V1. So this is now going from C to D along this infinitesimal path. Then going from D to A, dx is 0. So this expression will equal this minus this. These cancel, and we will have this minus this, so this gives us a negative sign. And we have the partial of v1 with respect to y. Adding these two together, that will be dy times dx. So this was our line integral. This part of the expression equals this. So remember this, we're going to need that in a few moments. But right now, let's consider this part of the expression and see what that gives us. So now we have v2 dy. Let's go back to our diagram. Now, dy is 0, so we're going to move this over in juxtaposition to the BC infinitesimal path, but that means we're going to move this to the right a distance of dx over 2. And going to the right, we'll consider that positive. So that means now that the v2 component, that's what we're concerned with now, that's going to change when we go from here to here, because the v2 component depends on the variable x, and we just changed that. So the new expression for v2, when this gets moved over to this infinitesimal path, this will be equal to what it was originally when it was over here, plus the amount of change. And that amount of change is how much v2 changes with respect to x. That's that partial derivative times the amount of change in x. And that is dx over 2 times dy. So again, we move the vector over to here to this infinitesimal path. When we do that, we're concerned only now with the v2 component of it, but that depends upon x, and we just changed that going to here. So the new component v2, when we go from here to here, is this, what it was originally, plus the amount of change. And the amount of change is that partial derivative that tells us how v2 changes with respect to x, times the amount of change in x. Then, when we go from here to here, dy is 0, so this is going from b to c. We're going up. Here, dy is 0. Now, we want to go over to here and go from D down to A. But now, when we move the vector to be in juxtaposition with this infinitesimal path, again, it gets moved by an amount of dx over 2. We went to the left. Left is negative. So now, going from D to A, that's in the opposite direction of from B to C. We're going down instead of up. And the component V2 will be what it was originally, plus the amount of change. And this is minus. And that will be then the partial of v2 with respect to x dx over 2, and that's times dy. So when we move the vector over to here, v2 is going to change, and this is what it will be. What it was originally minus the amount of change. And the amount of change, again, is that partial derivative that tells us how v2 changes with respect to x times the amount of change in x, and that's dx over 2. So when we add these together, and this now is going from D to A, these cancel. Minus minus, this becomes plus, so we have that v2 dy will equal partial of v2 with respect to x now it becomes this dx times dy. Now remember what we just derived a few moments ago when we had this. That was v1 dx. That equaled, it was negative. Then we had the partial of v1 with respect to y. And we had dy dx. So if we add these together, add this and this together right here, that gives us then the total line integral. So we have v dot dl, and that is equal to then this minus this. So we have the partial of v2 with respect to x minus the partial of v1 with respect to y dx dy. Now remember, our vector v, this is a three-dimensional vector. Now what happens if we take the curl of this three-dimensional vector? Now we had introduced the curl operation in one of our very first videos in this vector analysis series. It's taking the cross product with the del operator. So here's the del operator. Here's our three-dimensional vector. The cross product is expressed as a determinant like this. Then when we expand it out in minors, we have this expression. And let's look at the kth component of it. It's the partial of v2 with respect to x minus the partial of v1 with respect to y. So if we take the dot product of the curl with k, it gives us the partial of v2 with respect to x minus the partial of v1 with respect to y. And that is what this is. So we can say this. This line integral with a three-dimensional vector, that is equal to the curl of this vector dot k dx dy. Now this is not Stokes' theorem. And see, what we're doing is we're taking this, as we set this up, we were taking this line integral with a three-dimensional vector around an infinitesimal path. So around that infinitesimal path, the curl stays constant. So we have this expression, and this is an area here. So this is often written as a differential area vector, and we were in the xy plane with our infinitesimal path. So the unit vector k would be perpendicular to that. So this differential area vector, that's perpendicular to the particular figure that we're dealing with. But let's write this expression at the top, and with this, then we're very close to deriving the entire form of Stokes' theorem. So let's make some room at the top here. What we have right now is v dot dl, and that equals the curl of v dot dA. Now, let's see what this has to do with a three-dimensional figure. Suppose that we have a solid figure say it looks like this. Imagine that this bottom part here wraps around like this. So it's sort of like a basket type configuration. And we have it divided up into these differential or these infinitesimal paths. So let's just consider this expression for one of these paths. We'll call it P. And we're taking the line to go in a clockwise or a counterclockwise direction. But now let's think about this in terms of what's surrounding it. Here we're going in this direction to take the line integral, but in the one above it, we'd be going in the opposite direction. So with this common boundary, these two line integrals cancel each other. Here we're going down. For this one adjacent to it, we would be going up. So those two line integrals cancel. This goes up. Here we're going down. Those cancel. Here we're going to the right. In this common boundary, we're going to the left. Those line integrals cancel. So for all the common boundaries, the line integrals just cancel each other until we get to here. Here there's nothing to cancel. Here there's nothing to cancel. Here there's nothing to cancel. Down here, there's nothing to cancel. So we have this. Remember, this wraps all the way around. So if we add all of these up, all of these p's, what we end up with is taking the line integral about this closed curve. So adding these together gives this. V dot dl about the closed curve. Now here we were adding all these differential areas together. And that is what a surface integral does. Like this, and then this indeed is Stokes' theorem. We're taking the line integral of a three-dimensional vector involving some solid figure, and that is equal to then the surface integral. We take the dot product of the curl of that vector with a differential area vector. And here, like for this one, it would just simply be that dA being normal to this or perpendicular to that particular differential segment there. So this is always perpendicular to our figure. But that right there then is Stokes' theorem well, it's a three-dimensional theorem then. What we had before involving Green's theorem was like a two-dimensional analog of Stokes' theorem. Stokes' theorem involves three-dimensional vectors where we're taking surface integrals. But anyway, hopefully that makes sense. In the next videos, we'll work some specific examples using Stokes' theorem. The playlist for all the videos is at the website at digital-university.org.